We're going to look at the system flow of our manufacturing system. First, we'll begin with a material flow perspective. Here we see that material is flowing through our manufacturing system, and that's based upon your material flow process chart. And then we created the from-to frequency matrix, and that would indicate areas of high traffic corresponding to the highest frequencies, as well as the low traffic areas that would not be much of a concern. Certainly the high traffic areas are a concern. We don't want congestion in our system. The amount of material that we're moving is based upon the unit load concept, and each time we transfer our material from one location to the next, we're going to end up with the number of units based upon that unit load. Our flow rate has to be satisfied by the material handling devices. In other words, we have to be able to create the type of flow that will support the material moving into our individual workstations. So if we observe our workstations, first we see material entering the workstation, and after the process is complete, the material leaves that workstation. If we look at the entire system, we see these macro flow patterns. The first and simplest flow pattern would be a straight pattern, and these can be relatively long. I've seen them up to miles in length. And as you can see, we are going to arrange our workstations in a linear fashion. This creates traffic problems because if we need to cross over this linear flow, we may have to create other structures such as bridges and so forth, or move material up and over into a upper level of our facility in order to pass over these workstations. So it can cause traffic problems, but as you can see, it's very efficient in terms of our layout. It uses a minimum amount of area here. Typically, what you tend to see in most facilities due to evolving manufacturing systems and processes that are either added or removed from the system is more of a serpentine type flow. It also takes into account building constraints such as existing office areas, maintenance areas that can't be moved. And so we have these building constraints that we have to move around, so we create this serpentine flow throughout the facility. It works fairly well even with a large number of operations, and we can fit our entire system into a more compact area, and therefore we get rid of some of the traffic problems in the straight pattern. U-shape is also quite common because we can begin and end on the same side, and this helps with material flow when we come into our system and when we exit the system in the same area. Circular flow tends to be some type of loop structure. We'll see an example of that. And we begin at one location and then return to that location and then move to another location such as storage or shipping areas. A random flow is what you're going to see in more of a job shop or flexible manufacturing system, and these tend to appear random except for building constraints. Typically, you don't want this kind of flow because it tends to produce chaos. If we look at our individual workstations and how we're flowing between those workstations, we've got two possibilities. One is to move, as you can see here, our material from one workstation to the next workstation, and then we can bring in other components from the aisle, so I can transfer that through some material handling device and come into our workstation, and we add our component in this process. Or what we could do is make the workstations independent of each other. As you can see here, this is more like a flexible manufacturing system. We bring our material through the aisle and then transfer it to the station. So if I want to go from this workstation to this workstation, then I have to move to the aisle and back to this workstation. So it provides some independence and some flexibility, but as you can see, it increases the traffic requirements and therefore requirements for capacity in our material handling system. Inside the workstation, we've already seen this flow, and depending upon how we've set it up, we're going to have areas, as we can see here, to collect the waste from the process, and then once we have that waste, we need to do something with it. Is it going to salvage? Is it going to the landfill? This needs to be determined how we're going to deal with this because, again, it's material flow. We also have material flow into a rework area, and so is that attached to the process, or do we have one rework area for multiple processes? That will affect the traffic going between our workstations and rework. And of course, this represents the working process going on to our next workstation, which we already covered in the inter-workstation flow. So in the ideal world, we have a flow coming from receiving. By receiving, we mean material that's coming into our manufacturing system. So this would represent some type of storage area. We go into our production area, and then finally we leave with our product and go to the finished goods area or shipping. So in a perfect world, that would work well. But the reality is we tend to add storage here to deal with the uncertainty. And the uncertainty is in our production area, it's in our supply chain, which corresponds to our receiving area, and it's in the shipping, which corresponds to customer demand. So we have three primary areas of uncertainty that result in a certain amount of storage here. So if you think about the uncertainty in the production area, that has to do with scrap, that has to do with variation in cycle time, and other factors that cause us to change our production rates, the scrap rate, the time in the system. As a result, we're going to have to provide some work in process inventory, or we will not be able to keep up with the demand. And of course, the finished goods provides us as a buffer to our customers. If there's variance with the customers, then we're going to have some storage area for that. And that could also include seasonal variance as well. The raw material inventory, the size of this storage area will be proportional to the amount of uncertainty in our supply chain. And that's based upon whether or not our vendors can deliver on time. So case one is fairly straightforward. We have a nice pace system here where we receive our material, it goes through production and goes out the door to our customer. So that's a perfect world. We don't require any storage because the material is immediately being processed and sent to our customers. But life is rarely perfect. And so when we have some variation in our rates, we're going to have to accommodate that with the inventory that we just mentioned. So here, as you can see, we have changing levels of inventory that are dealing with changes in our supply chain and or changes in our customer demand rate. In case three, we can see here finished goods is a lot larger in terms of size. And that is telling us that our customer demand is fluctuating. And so we need to accommodate them by having enough inventory to deal with those times when we're going to have high customer demand. So as you can see, the amount of storage will depend upon that uncertainty. If I have problems with my supply chain, I'll have to increase the raw material inventory to deal with that uncertainty. In order to reduce your uncertainty, you have to have more reliable information about your supply chain, about the production area, as well as your customer demand so you can match and we don't get this kind of effect. Now, as you can see here, what's happening is as we build up our inventory and finished goods, that is going to back up into the work in process inventory of our production system, and that causes a connection or dependency between those two areas. Here's an example of a serpentine flow pattern that is arranged in a circular fashion. As you can see, we've got a overhead power and free conveyor, and the rectangles here represent carriers on the conveyor. This region here represents a loading area where we bring in our material loaded onto the carriers. It then moves through the power and free conveyor to our first process here, and then our second process, third process here, and fourth process. And then finally, we have a staging area here where we do some additional assembly. And then our final process here, leaving that, we go to an unload area here. So as you can see, it's serpentine, but we sort of end up in the same area as where we started. And so this is a common configuration when you're dealing with flow that you want to originate and end in the same area. Here's another example, a detailed design. It just so happens in this case that we've got a storage area here representing our raw material. And then in this region over here, we have our actual processing. Now, if you just think about this system design, you can see a very small percentage of the total system is devoted to the actual processes. What we have here are finished goods, and these are going out to the customer. Here are the docks filling tractor trailers, and they'll be shipped to the customer. Over here we have receiving. Well, right off the bat, you should notice that we have a fairly large area devoted to the storage of materials, indicating we have a problem with our supply chain. So if we want to reduce that, we're going to have to reduce the variability of the supply chain. It appears because of the footprint here, we don't have much work in process storage, and so that indicates that our production system has very low variance, and that's a good thing. However, here in our finished goods, we have a significant amount of product being shipped to the customer, which tells us that our customer demand is highly variable. So we're providing a significant storage area to deal with that variability. If you look at the individual locations in these designs, what you tend to do is to relate one region to another based upon the strength of the relationship. And so this relationship chart is a common mechanism used to describe those relationships. As you can see here, I have a set of processing areas that we're going to use to add value to our product. And then we have some storage areas and then the maintenance area. In my matrix here, I'm going to indicate, and this is obviously either an upper triangular or a lower triangular matrix because the relationships reciprocate with each other. I'm going to indicate the strength of the relationship just using letters here, discrete categories. So we can read this and say that between raw material and stamping, I have an absolutely necessary relationship, which means that I'm going to place the raw material storage area close to the stamping area. And we also note in the lower half of the square the transfer frequency corresponding to the material flow moving from between those two areas. Now in this case, it'll obviously be moving from raw material to stamping. So what this allows us to do is to get an idea of how we should set up our system flow, recognizing the relationships between the various areas in our system. We can also use flow measures from the actual material flow. And the two main ones are frequency that we've seen before. That can include the average, which would be the magnitude of material transfers, as well as how variable it is. For the distance, in terms of location in our facility, we can look at the total through the entire system, all the parts, the average distance traveled per part, so you tend to like to minimize that. You'd also like to minimize the variance of that distance that traveled. And then the individual moves themselves. If I look at a part, how far does it travel just for that individual part? So these are measures that we can use to try to quantify the amount of traffic and whether we have poor flow or good flow in our system. Attributes that you want to consider in your total system design, of course, products, which we mentioned before, can be highly variable. The mix of products, so what percentage of all the products does that product consist of? Then the volume, how much of that particular product is actually being produced in some time frame, and of course the routing sheet, which corresponds to the material flow process chart. The processes, as we know, have physical constraints, which will end up being a footprint in our facility. They have a certain amount of capacity to produce parts at that location, and there's a relationship, as we've seen, to the product based upon the material flow process chart. So if we go back to our individual process model and we incorporate that at a system level, what we see is flow starting at the first station, J, and then moving to the next station, J plus 1. And if you recall, we have the probability of rework, and then small s here is the scrap rate at this workstation J. Well, as you can see what's going to happen here, we've seen this calculation before. If I put xi into the system, then this is what I get out of that first process. Well, this becomes the input to the next process. And if that becomes the input, then we end up with this being the expression based upon this amount going in. How much do we get out? Well, that, of course, is based upon the rework rate at the J+1 process and the scrap rate at the J+1 process. So if you keep progressing from J+1 to J+2 throughout your material flow process chart, we are essentially taking the product of our 1 minus Sij times 1 minus Rij. And of course, that's what the cap pi means. We'll multiply all these quantities for all the workstations that we're going to go through. So if I put Xi into my entire system now, not just one individual process, I will get Ni out of my system. Based on the same principle that we use for the process model, but now for the system, we see the relationship between scrap rate, the rework rate, and the amount coming out of our system. If, of course, we can rework everything, R sub ij is equal to 1, then all scrap can be reworked, and we just end up with N sub I. Of course, if we multiply these together, you can see we're compounding the effects of scrap rate and the rework. So let's look at a simple example. Let's say I want to produce 1,000 good parts, and I have 5 workstations that I have to go through in sequence. And for right now, we'll just assume that the scrap rates and rework rates are the same at each station, even though they won't be. So I take my 5 workstations, and now I need to multiply my S sub ij times 1 minus R sub ij, and then take the product of all of those for each of the workstations, divided into 1,000. That tells me how much I have to produce. Well, we can do that. We can vary the scrap rate and the rework based upon multiplying those. It's just taking the exponent to the 5th power. So if I plot that and vary the value of scrap rate, we see here the region for X sub I, and it shouldn't be surprising that in this red region up here, we have a very low rework rate and a relatively high scrap rate of 0.1 to 0.2. Well, you can see the profound effect here of the multiplication of all the workstations. If I want to produce 1,000, remember N is equal to 1,000, I'm actually producing close to 3,000 up here because I'm going through all those workstations, even though the individual scrap rates are less than 0.2. So really, you'd like to stay down in this yellow region here, which means if you're operating at low scrap rates, it's fairly insensitive to that rework rate. But as that scrap rate increases, then of course you're going to want to push towards higher rework probability. What about the work in process that we see in our system? And as we said, that can vary quite a bit. The best way to look at that is the average number of product that we have in our process. And as you recall, Little's law gives us a way, no matter what our system looks like or is configured, it's a universal law that on average tells us something about the flow. So if you remember, L is the number in the system, lambda is the rate at which we're moving through the system, so we can think of that as the inverse of our cycle time at each workstation, and then W is the time that we spend in our system. So in our context, what that really means is our work in process is equal to our production rate times the manufacturing lead time. And so I can apply this across my system as a whole, or I can look at individual components of my system and determine what the work in process is. Now, of course, if I look at my system as a whole, my R sub P, my production rate, will be based upon the bottleneck workstation. And I would have to know something about my manufacturing lead time, the time from when I enter the system and exit the system. Based upon those two values, I can calculate the amount of work in process. So when you think about removing that work in process, remember we said that that storage area will be based upon the variance. We should be worried about the variation that could occur in our production rate here. And so if we have high variance, we're going to have to increase that work in process. If there isn't much variance, then we should be able to decrease that work in process. Now, if I look at the right side of the expression here, the best way to decrease your work in process is to decrease the manufacturing lead time. Obviously, you wouldn't want to decrease your production rate because that's a measure of how well you can match your customer demand. So whenever you think about your system, you should always be worried about the fluctuations that can occur due to uncertainty and variance in different aspects of your system. You should also pay close attention to the flow pattern and there are trade-offs that you're going to make depending upon your configuration. The cumulative effect of scrap must be understood, otherwise you're going to underestimate the amount of material that is going to have to be processed by your system. And also you may assume that small scrap rates at individual processes will not contribute to that overall scrap rate, but as we could see in that example, that will be a problem. Flow patterns affect the plant layout, and that will be based upon your material flow process chart. So you want to pay close attention to how your material is flowing and how that relates to your individual areas of the plant. Obviously, high traffic areas should be close to each other so that you're not transferring material large distances at a high frequency. We need to compensate for uncertainty, as we've seen with inventory, and that has to do with the raw material, the finished goods, as well as the work in process. It has to match. So when people say, let's minimize the inventory, that's fine as long as you minimize the uncertainty at the same time. We've seen that the system topology, our individual processes, and the material transfers will all affect how material is flowing through our system. And don't forget Little's Law, that's a good rule of thumb, can give you a way of estimating the characteristics of your system.